maybe we'll wait a little bit more because they're raining. Any question from yesterday or regarding your revision for the quiz? You want to last minute settle now? Any questions you want to ask from yesterday? Or any issue you met during your revision? Hmm? Columns and slope of C. In a matrix, start with a matrix or basis? Three, yeah. And then three vectors are linearly independent. Okay. This is for random three vector. Is it? Where is the vector live? Vector belongs to what vector space? Three vectors three linearly independent. Like this. So where does vector live in where? Anywhere? Anywhere? Any vector space? Where does vector live? Live in Pn, Rn, or somewhere? Or any vector? Huh? Arbitrary. Okay. You want to fix, but you want to fix R3. You want to fix R3 here. Okay. Okay. So the question is, if you have a three independent vectors, linearly independent vectors in arbitrary V, okay, arbitrary vector space in space. So does it form a basis for R3? Basis in R3? So the answer is no. No, right? Because let's say if I take, how about if I take one t and t squared? Okay, perfectly good linearly independent vector in where? P2? Yeah, P2. Okay, but this is not a subset of R3, not an element of R3. Does it make sense? Does it make sense? Does it make sense? They can live in different space. Okay, but what is true for this? But what is true for this part here? Let's say we call it V1, V2, V3. Let's find out what is true. So what is true here is if we take the span of V1, V2, V3, okay, the linear combination, the subspace spanned by this three vector, then this is a three-dimensional subspace in the, okay. If you consider their linear combination, they form a subspace in their vector space, which is three-dimensional. Not R3, but three-dimensional subspace. Is it okay? Or you still have question want to follow up? Anjing. Oh, the vector have three entries. Okay. So if the vector have three entries, then that means this one the question one. If the vectors have three entries, then that means your vector doesn't live in arbitrary vector space. So you just has so this question will make the question easier. So three linearly in R3 form. Yeah. So this is by the theorem in class, where if we take n linearly independent vectors in n-dimensional vector space, then they form a basis. By theorem, n linearly vectors form basis in and yep. So 3 linearly independent vectors, 3 and 3. So that means you have every column have pivot, every row have pivot. So you span a linearly independent. Huh? 4 vector, uh-huh. 4 vectors, no condition of vectors. No condition. Huh? Linearly independent. 4 linearly independent vectors in R3. Uh-huh. Does it also form a basis? Okay, very good. Does it also? Any idea for the rest? If you have 4 linearly independent vectors in R3, does it also form a basis of R3? Must have a free variable. Correct. So if you do row reduction, you must have a free variable. Right. Okay, let me draw the picture out first. 3 times 4 like this. So something like this. Anything here, everything above here. Okay, must have a free variable. So what does this mean? This means you can never find 4 linearly independent vectors in R3. You can never do that. You try very hard. Try for a week, you also cannot find. Try for a year, also cannot find. However, you cannot find. Okay. So in R3, at most you can find 3 linearly independent vectors because this is the dimension of R3. So you can never find 4 linearly independent vectors because dimension of R3 is 3. Yeah. Remember, dimension is an invariant. You cannot more than it, you cannot less than it. True. You can find 2 linearly independent, but they don't span. Okay. So you increase until 3, they are linearly independent, they also span. Yeah. Who? Oh, Zhao Jing. Where's Zhao Jing? Zhao Jing not here yet. Okay. Yeah. Yeah, this is how you learn mathematics. Try change some word, some space. Try change some number. See what happened to the statement. And then when you try to play around with the variable, you understand what's going on. Okay. Okay. Before you sleep again in the lecture today, I want to give you a pill first. Okay, I give you a pill, medicine. I give you a pill. So the medicine is like this. So when you listen to what I say, right, don't just absorb. Absorb like a sponge. So you keep absorbing the sponge until a limit the sponge cannot absorb already. Okay. So what you need to learn is to digest. It's like you eating, right? You eating, you have to digest. If you don't digest, can you still eat? You'll feel full. Okay. So every day you digest and then you throw away. Okay. So when you listen to what I say, right, try and digest what I say. Okay. Don't just absorb everything what I say. Okay. Everyone have a limit on. If you absorb food, what do you do when you feel full after eating? Sleep. Same. It's the same. So you absorb food, then you sleep. I know your skill of absorbing is very good because I'm also from that kind of learning. Just teach you how to do, calculate, see this, do this, see this, do this, see this. This is good. Okay, very good. But now you are in university now already. Okay. So after university, you are meeting with unknown. Okay, a lot of things you don't know how to do one. Okay, the difference between you and me is I know the answer, you don't know the answer. That's all. Yeah, seriously. Okay. So so try to ask me to suck. Okay, I give you a chance. Some lecturer don't let you ask one. Some lecturer they just right. Just say, and then finish, go home. Okay. So try to interact with me and then give me feedback. And then I will know better what you want to know and what you don't know. Then I will give more appropriate content. Okay? Understand? Okay. Uh, yeah, yesterday the proof of the theorem. So let me state the theorem. So if you have a V1, yeah, with distinct vector, eigenvectors with distinct eigenvalues, L1 not equal to L2 not equal to n, they form a linearly independent set. Okay. First time I thought about this theorem, I said this is an important source of finding a basis. Okay. Then yesterday we tried to prove this theorem. I think I screw up a bit because it's not as easy as I thought. Because why? Because this theorem actually is a bit technical. Okay. I will rewrite the proof in my lecture notes, and then you can try and compare to the textbook one. See you can understand better or not. But I think I promise this one is the most technical proof we will see in this class. Okay. It is not hard, but it is technical because the situation changes depend on vector space, depend on vectors. So how you combine all these situation together, so it's a bit technical. Yeah. Just technical but not hard. Okay. Since yeah. Yeah. And then summary from yesterday is okay. Another story is because new guy coming in just now. So another story is last semester. Last semester I got one student, right? He also come to my office hour. He also complained to me. He cannot understand what I say in class. Okay, at least he come to my office and then tell me. Okay, some of the students just ignore it. So I tell him, I and then somehow he got a mind change. He got a mind change. He cannot follow my lectures at first, and then until the last few weeks, he can follow my lecture. Not to say he understand everything I say, but he can follow. And then he can ask about questions, and also he can say maybe this part is it you say wrong or something like that in the class. Seriously, his result, okay, his result in midterm is 30 to 40 is what? E? Is it E? 30 to 40 marks. Is it E? Okay, let's say E. Okay. His result from E jump to A minus. Okay. It's just a mind change. It's just simply a mind change. Okay. There's not much change from me. I did change, but I didn't change much. But he changed. Okay. So it is possible. Yeah. Whether you want or not. Okay. Okay. Enough for story. So let's come back. So uh, okay. Okay, let's do summary from what we studied yesterday. So let's talk about an example. So what we did yesterday is we given a matrix, okay, we try to find the eigenvalues. We try to find the eigenvalues from the determinant of A minus lambda I, which we call the characteristic polynomial. So in this case, we have 2 minus lambda and 1 minus lambda, because we can use the property of triangular matrix. Using property of triangular matrix. And then we set this equal to 0. Okay. Set determinant of A minus lambda I to 0. And this is what we call the characteristic equation. Because we got the equation here already. So this means we want to solve for the equation. Okay. So when we solve for the equation, we get the root of the equation. Okay. So these are the root. Okay, let me use this. The root of the characteristic equation, which are the eigenvalues of A. Okay. So from here you can see that if it is diagonal, the eigenvalue are really just the diagonal entries. Okay. You can say that since you have a diagonal matrix, then the diagonal entry form the eigenvalues. Then after that, we will find the eigenspace. Eigenspace. Find eigenspace for lambda. So what's the eigenspace mean? What's the eigenspace? It is really the null space of wait, let me move this. Null space of A minus lambda. If you're not following, you should pause me now. I will explain what's going on. Okay. So find the eigenspace for lambda equals to 1 over 2, which is finding the null space of lambda I, A minus lambda I. So for each of them, we need to calculate what is A minus I. So A minus I in this case is 1, 0, 0, 0. Okay. And then the null space of this is what? X2 times 0, 1. Okay. So you read the parametric equation. When for lambda 2, what do you get? You get minus 1, 0, 0, 0. Okay. If you like, you can row reduce this to 0, 1, 0, 0. Where you get, maybe I put here V1, here V2 equal to X1, 1, 0. Okay. So so this is the eigenspace. So it solves the any scalar multiple of 0, 1, okay, is an eigenvector for 1. Every scalar multiple of 1, 0 is an eigenvector for 2. Okay. So what you can write is eigenvector vector for lambda is, you just pick 1, 0, 1. Okay. If you like, you also can pick 0, 2, okay, or 0, half, up to you. Okay, scalar multiple. And then the eigenvector for lambda is 1, 0. Or you also can put 2, 0. Or you can put any c time 1. Just pick one of them. Okay, so far, okay? So far following? Feel free to stop me. Okay, so and then yesterday we have a powerful theorem. That is, let me put 3. There's the diagonalization theorem. Okay. So diagonalization theorem says that A split to PD P inverse. Okay, so what's PD P inverse? So let's remind ourselves. So P consists of columns of eigenvector. And D consists of diagonals entries of eigenvalue. Okay. So far, okay. So what's good? Okay. Okay. So in this case, we have what? We have 2 eigenvectors correspond to different eigenvalues. So our A is what? Our A is 2, 3, sorry, 2, 0, 0, 3. Okay. We can pick the easier one. So maybe we pick 0, 1. Okay. So we pick, okay, maybe we put color here. So we put 0, 1 as the eigenvector for 1. Okay. And then we pick 1, 0 for the eigenvector for 2. Okay. So the position of eigenvector correspond to the position of eigenvalues. Okay. So what's P inverse here? So I guess easily we can get P inverse to be itself. You can try and compute. Try compute. Okay. Then we will write. Sorry, what's this going on? Wait, sorry. Okay, sorry, I copied the wrong question. This is one. Okay. Okay. So I split my A into a diagonal matrix. So here is a diagonal matrix. P. Columns of eigenvectors. Okay. So why is this invertible? Because they are linearly independent. Why they are linearly independent? Because they are eigenvectors for distinct eigenvalues. Okay, so that's why I insist on proving this, because this is kind of important. But if you don't appreciate the proof, you need to know this result. Okay, you need to remember this result. Every eigenvectors you get from different eigenvalues, they are linearly independent. You need to remember this result, at least. Okay. So if you have different eigenvalues, you get the eigenvectors out. They are all linearly independent straight away. No need to check one. Okay, because in the proof already checked for general cases, so you don't need to prove in the real situation. Okay, So that's why our P is invertible. Okay. And yeah. Okay, and I mentioned. Okay, let us stop here first. Okay, there's some issue with algebraic multiplicity, geometry multiplicity less than. There's some issue going on here, but maybe we won't talk about it today first, later too much. So maybe I'll bring this issue out next time. Okay. There's some issue if we regarding geometric multiplicity less than algebraic multiplicity. You can read about it first, but I will try to bring it out next time. Okay. This one for next time. Revise next time. You can try to read about it, but I will revise next time. Okay, so far okay. So given the matrix, try and find values. After you find the eigenvalues, then you got eigenvectors. If you got the eigenvectors and linearly independent, form P, take P inverse, and then diagonalize your matrix. Okay. Okay. So far okay. Okay. So today we want to understand what is really A equals to PDP inverse. So what is it going on geometrically? Okay. So what's going on with PDP inverse geometrically? Okay. So need to tell story again. Motivation. Okay. So the motivation is, let's say we want to start from any vector space V. Okay. Any vector space W. And then we got the map. We got the map E. Okay. So T is a linear transformation because it's a map between vector space. Okay. Right. So far, okay. I just give a map. Okay. So I map the vector here into a vector in W. Okay. So far, okay. 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 So let's say we have a extra condition. Okay. We got a basis on V and W. So they are finite dimensional. We list down the basis, B1 up to Bn for V. And then for W, we also have a basis, C1 up to Cn. Okay, so it is a linear transformation between finite dimensional vector space. Okay, okay. So what we can do, we learned that finite dimensional vector space is isomorphic to what? Remember? Finite dimensional vector space isomorphic to what? Yeah. Finite dimensional vector space. We can take the coordinate vector. We can take the coordinate vector. So the vector space are isomorphic to. And take coordinate vector. So where do we land in? Land in where? Anyone remember? If we have a vector space with n basis vector, after we take coordinate vector, what do we get here? What do we get? Okay. So let's for example, okay, let's take this x to be a0 b1 plus a D2 up to n. And then, so what do you get? What do you get after you apply coordinate vector? What the coordinate vector? Yeah. A1, A1, A2, up to AN, right? So you read the coefficient. So where this guy live? Where this guy live? Rn, good. So we land in Rn. Okay, so you see, just now I used so many words to describe one process. The process is called finite dimensional vector space is isomorphic to Rn. Can you see it? So when I say a finitely dimensional vector space is isomorphic to Rn, it includes so many processes here. Okay. So this is one of the good things about abstract. Okay. I use one word to describe so many processes. I don't need to say express your x in your basis first, apply coordinate vectors, get the coefficient, and then see where the coefficient lies is Rn, so these two are isomorphic. You know? So I use one word to conclude everything. When I say finite dimensional subspace, a vector space is isomorphic to Rn, that means if you express your element in V, okay, in terms of basis, and then you get the coefficient out. This is what you do. Okay. You get it? Now? Okay. Maybe you try to practice more. Try to practice more, then you will learn it. Okay. So next, how about on the right side? Okay, on the right side here. So the coordinate vectors sends elements in W to where? Where's the space here? To where? You want to repeat again? So we got a basis C, right? Okay, we got a basis C, and then we need to rewrite our element in terms of the basis C. Maybe B1, C up to A2, C up to A. Sorry, why use A? B, Bn, Cn. Okay, so you get coordinate vector again. So what do you get? Do you get? I don't want to use B dash. Use what? Use D. So what do you get after you get the coordinate vector? Coordinate vector. Coordinate vector for Tx. What do you get? Game already. Coefficient. Okay. So coefficient is just D1, D2 up to Dn. So where this vector lies? N again. Okay. So you can see that this Rn is just depend on the number of the basis vector. Okay. Because we got n of them here. So we got map between E and W. Okay. We also have map between V and Rn, W and Rn. Okay. So there's actually one not obvious. One thing we can try to ask here. Okay. Can we complete the square? Right. Is there a bridge going from this Rn to this Rn? Okay. Can we complete this bridge here? Change of basis. Not so fast, not so fast. Okay. Yeah. So can we find a map like this? Let's call it M. Okay. Because it's mystery. So we call it M. Yeah, mystery. So let's see we can find this m or not. Okay. So let's see if there's an m here. So what's the mystery here? So let's write down what we have. So let our x be equals to a1 b1 as what we started just now. Okay. So we apply t on it. T is a linear transformation, right? So let's apply t on both sides. Apply t on both sides. And then since t is a linear transformation, then we can write a1 tb1 up to a2 tb2, so on. Okay. This one, if you wonder, this is plus y equals to x equals to c. Or in one word, t is a linear transformation. Okay. So what can we do next? So we can apply the coordinate vector c. So apply coordinate vector with respect to c to both sides again. Okay, see where it lands. Okay, so we got an x from here. Okay, is it like this? Okay, x, and then we map it to w. Okay, and then we try and take this map here, go down, see what we get. Okay, let's see what we get. Oh, let's see what we get. Apply coordinate vector relative to c. What do we get? We get a1 on eb1 c plus plus an tbn. Okay, so this word, because this is again, coordinate vector is a linear transformation. So what's this? This is a vector equation again. Okay, so a vector equation is equivalent to matrix multiplication. So we can collect the vector together and form the matrix. So we can collect the vector together and then form the matrix. Okay. So here we got a1, a2 up to a. Okay. Vector equation, matrix equation. Yeah. Then this is the thing that we call M. Okay. So let's see, is this doing what we want it to do? Okay. A, a, a. How do I show you? Okay, maybe make it smaller a bit. Size. Okay. So see what do we get? So now we get that t coordinate vector of tx relative to c is equal to a matrix times this. So what is a1 up to an? Still remember, a1 up to an is what? Is the coordinate vector of x with respect to v. Okay, so you got a matrix times coordinate vector with respect to b, and then you get coordinate vector with respect to c. Okay, so coordinate vector with respect to b, and then coordinate vector with respect to c. So this is the M we want. Okay. Okay. So far, so good. Okay. So what we define is if, see, is it here? Okay. Yeah. So if we have a V and W of dimension M and M, okay, you can change M if you like, change the other dimension. Then you have basis for C, B, and C. Okay, just now we have B and C. If T to V to VW is a linear transformation, then there's this matrix M times N such that the coordinate vector of Tx relative to C is equal to M times coordinate vector relative to B, and then we call that M is the matrix for T. So let's highlight this definition. So highlight this part, matrix for T relative to B and C. Okay. So how do you find M? So the way you find M is you apply T to the coordinate to the basis vector on B, okay, and then you take coordinate vector relative to C. So something like this. So T. C. Okay. Okay, I realize that there's a lot of words here. Okay. Maybe one reason you confused is because you are not familiar with this definition yet. Okay. So I think that's fine, that's normal, but you just need to get what? Get used to it. Okay. Just need to get used to it. Okay. Yeah, you need to get used to it. It's normal because this concept seems new to you. So all the word is like new word, alien word. Yeah, so you need to get used to it. But sometimes I will point out the key point. So the key point you have to really get it. When I say, okay, for example, I say M is this thing. This thing is very important. So this thing you must know first. Okay. After you know this, and then go and dig up what is the rest. Okay. So start from the key first. I'll tell you the key. So you go get the key first, and then you go and try and find out the rest. Okay. I want to tell you everything, but I cannot time permit. Okay. So how about okay? How about we take a rest first and then we come back, for example. Okay. Come back at 9. Okay. Then
那个不是这一课，那个重要就是这个地方我不太懂。
你讲我算出来是什么？
不是，我是说这个地方我看的时候我看不太懂这个是干嘛，就是这个你怎么来？
equating the coefficient of the two polynomials. It's okay. 其实我是说 equate coefficient of 这一边跟这一边，所以其实你要的话，你要撑开它先。 但是你不要撑开的话，你直接看就知道，反正你撑开跟看也是一样的。比如说啊，你如果把它们放在一起，不是你是会把 constant 放在一起，对不对？所以如果你把 constant 放在一起，你看哪一个是 constant？这个跟这个 ，OK？所以你看 C1 加 2C3 等于3，对，出来了哦。那第二个是 T 的咯，看谁有 T，这个有 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 T，所以这边是 C2 减掉2C3等于1哦，然后一样哦，这个1、2呀，如果你把它拆开又放在一起，也是一样的东西。
好像是第7，
你要这样子做一次，
好像第7还是第6，我忘记了，
嗯哼
有一个地方算错。
算错了，你告诉我，我会改一下，然后看上去。你找到了再告诉我。我有更新了，你有看到吗？
知道，但是
还是错了
说你那个地方还
还是错
错，
我
不知道，不知道跑哪去了。
再找到再告诉我。你直接发给我也是可以。你直接看到就发给我。哦，我改了，这是谁告诉我的？是你告诉我的？哦，不是，有人告诉我，我改了。看一下，
这个 dimension 就是3了。
对，没有错，这个是 lecture 题啊。昨天有人告诉我那个，我好像改了，但是不知道放上去了没有。赶紧继续，我改了那个。
这个
Yep，
这个
T
A 是2，然后它那个题目，我这个rank A 是4嘛，他说那我这个扣 A 不等于 R4 since 扣 A is a subsystem。
对，
是吗？为什么是 subsystem？
是 dimension 的意思哦。
对啊，
是 dimension 跟 R4是不一样的东西啊。
之前不是证那个就是 basis 的时候，就说如果它如果它的 dimension 已经是 n 的话，那我只要证它那个只要证 span 在v1到 vn 上，或者是 v1到 vn 是 linearly independent。
对。
我这个，那你看我这个就是 n 个吗？如果 span 在上面的话。
但是我是说，这些 vector 可以活在不同世界，不一定要在 R4，它可以在 P3啊，它可以在
对这个 R4和 P3，它们两个其实本质不就是一样？
本质一样，但是它们不一样，那 element 都长得不一样。
P3的 element 意思就是它大概是它的standard 就是这样T
没有错，没有错，yes，
是这样的。
对，长得不一样。
对啊，是长得不一样。
所以他们活在不一样的世界里，但是他们是 isomorphic as a vector space。
他们计算的时候是一样的，
计算的时候是一样的，但是他们一开始就不一样。
我这个 dimension，你看我这个 dimension 是 n 啊，然后我 span 就 span 在，那我 span 的话，那
但是你要知道它的 column A 长怎样先呢？它 column A 长怎样？
它 rank A 已经是4了。
没有，你先回答问题。它的 column 躲在哪个世界里？
没有说呀。
有啊，一定有的，因为我这里写是 R5，所以它一定是一个5乘什么东西的，5乘。
就是我假如说我这个是这样的，就是1、2、3、4，就我这个比假如说是0，
它应该是5乘7， 我没有错，哎，乘6，它是5乘6哈，它是5乘6的那个5乘6的 matrix。
对，5乘6，因为这个是6
呀，对对
所
对对对，
以就有6 column。
对对对对对对对对，
那就是
所以你看它的 column vector 活在什么世界？明白吗？
它是5乘6，也就是说它虽然是 rank 是4，它只有4个 pivot position，但是它的还是它虽然这一行是0，但我这样算的话，它的
它活的世界不一样，它是在 R5里面的 4 dimensional subspace，它不是 R4 在 R5里面，它是4 dimensional subspace 在 R5 里面。
虽然是，但它不是，
是什么？
就是它那如果我找它的 n 的话，它的 n 确实也是 4，
什么 n？
就是如果是它的 dimension 呢？
对对 dimension of rank A 就是 dimension of 它的 column space，就是4咯。
4就是我这个 dimension n，
它是一个4 dimensions 呢 subspace 活在5 dimensional space 里面。
这样说的话就是 dimension 4，但它是 R5的 subspace。
Yes。
那就还是要看这个。
Yes。要看它在哪里，在哪个 vector space。
像刚才讲的就是如果有more vectors than entries in the vectors，这个就是那个嘛，然后它因为它它的 dimension 它的 n 只有3啊，但它有我记得它应该是有4个不同的 vector，这个其实
3个
4个，就是它是在
R3嘛。
R3的世界，但它给了4个。
哦，对对对对对，就是这个1、2、3、4这个。
给了4个，
然后呢？
不是他就是刚才上哥讲的，这个那我这个4肯定是
肯
linearly
定 yeah
linearly dependent 的呀，
肯定。
这些 vectors must be linearly independent。
没有又写错了 ，sorry， 我又分不 OK， 告诉这个是什么地方？调一下，我好几个有这样的错误啊，independent 不 independent 不分的，在哪里？这要改的，很严重。
是的，我看一下这。
哎，我觉得你这些问题很好哎，你在那个 lecture 前问可以吗？
我刚把它就整理了一下，这昨天的分析。
下次在 lecture 的前问一下，我觉得很好的这个问题，应该会解答他们很多问题。
一个
7还哦，第7，要刚才那个波开要告诉我好多问题。
还有我昨天还算的时候就好多，就是数字有一点问题，但是就是思路都没有问题。
OK，不是你告诉我，我直接改掉。如果你看到了，
这个
看到了，
这个
must be linearly dependent。不知道3清是看到这个乱的。
哦，对，这个就是我看了一下，就是它这个，哎，有一些是我感觉是数字有错。我再找一下。
OK，你找一下告诉我，直接发给我，你直接发给我。Hello.
Start another story. Okay. So why are you in university? Why not just go and work? Yeah. So method is very important. I don't deny that you don't learn method. Method is very important, but Another thing important you come to university is you have to come and think. Okay. So this is, for example, my brother. Okay, my brother is an engineer. So this is the difference between mechanics and engineer. So mechanics, you just do what the engineer tell you to do. So mechanics will do the work. Engineer have to think how to do. Okay. I don't say that all mechanics don't think. I just say that this is the nature of the work. Okay. For example, my brother, after graduate, he's an engineer. He go and work. His salary is higher than the mechanics. But mechanics is the one who know how to do. But my brother is a new engineer. He don't know how to do. Actually, the mechanics know how to do everything hands-on. But his salary is lower than the engineer. Why? Because the boss think that the engineer know how to do, know how to improvise, not just do. You know what I mean? You know what I mean? Yeah, think about it. Think about it. Okay. I don't say that method is not important, but you also need to learn how to think. Okay. Okay. Continue. So, yeah, so continue this example here. Okay, so this example here. So suppose we got a B for the basis V and C a basis for W. So we got a map from to W, okay, a T. So we got a basis B1, B2, C equals to C1, C2, C3. Okay, whenever you read the question, right, I like to write into something that makes sense to me. Okay, turn the question to something that makes sense to you. Okay, and then we have a map sending B1 to 3C1 minus 2C2 plus 5C3. B2 to 4C1 plus 7C. Then the question is to find a matrix M for T relative to B and C. Okay, just now, what have we learned? So the key is what? The key is this. So if you want to find the M, you need to know what T does to the basis element. Okay. First of all, you need to know what T does to the basis element and then express it in terms of C. Okay. So here already tell you how T apply to B. Okay. And then you need to change this according to the coordinate vector for relative to C. Right. So can you try work it out? What is M? Work it out. What is M? How about tell me what's the size of M first? What's the size of M? 3 times? 3? No. Not 3 times 3. This is a map from what dimensional vector space to what dimensional vector space? By 3? No. Close. Dimension to what dimension? This vector space. This linear transformation. 2 to 3. So the matrix have to be 3 by 2. Okay. So you swap 3 by 2. Okay. Remember the matrix add on here. So it's 2 by 1, 3 by 1. So always the domain come later, 3 by 2. Okay, so what is TB1 with respect to C? What's the coordinate of TB1 with respect to C? So what is TB1 with respect to C? TB1 with respect to C. 3 minus 2 and 5. Here, 3 minus 2 and 5. How about TB2? So this is the matrix you want. So make sure when you want to find this matrix, right, get your basis out, get your transformation, add on the basis, okay, and then read out the coefficient column by. Okay, next. Okay, next, let's say we change our W to V. Okay, look at the Seng space. Okay, change between the Seng space. Okay, and then we also have a basis for V. So we also have a basis for V. And then now we give the new name to M. We call it TB. Okay, TB the V matrix for T. Okay, so we let M for M TB. Okay, T is between the same space. Okay, so we will see in a moment why we call it TB. And then this is related to what Singpeng say, change of basis. Okay. This is just naming, just naming. If T is between V and V, we call it TB. And then B is the basis for V. Okay, naming first. I don't tell you why, but name it first. Okay, next example. T, a linear transformation, Pn to Pn defined by, if I give you this general element, okay, add on it, what I get A1 plus 2A2. Okay. So first of all, we need to check whether this is a linear transformation or not. Okay, because we only care about linear transformation. So remember what we do for linear transformation? Do you still remember? We need to show any x, y in P2, tx plus x plus y equals to tx plus ty, okay, and x equals to c times tx. Okay, check these two things. Because maybe time constraint, pick one if you want to see which one. First one. Okay, yeah, first one I think is the hardest one. Second one is easier. So second one you can try out. Second one is easier, but first one is hardest. Harder among the two. So let's try and do the first one. So if I want to do the first one, we need to write x in a general form. So a0 plus a1t plus a2t squared. And then y is equal to b0 plus b1t plus sum of a0, a2, b0, b1, b2. Okay. So what is tx plus y? Okay. So tx plus y is just really you add up two vectors, right? Okay. Okay. So can you do t on this thing yet? Okay. Can you do T on this thing? This long thing? But you only know how to do with three-term summation. So you need to make your element into this kind of form first. Right? So that means you need to factorize first. Okay. First, A0 plus B0 plus A1 plus B1 E plus A2 plus B2. Only now you can see that these two terms are similar. Okay, it's some constant plus some constant times t plus some constant times t squared. Okay, from now only you can apply t. Okay, if you apply t, what do you get? T is equal to, sorry. So what do you get? So you pick the coefficient for t. Okay, so which is A1 plus B1, good, plus the coefficient of t squared. So 2 times A squared plus B squared. Right? Times t. Don't forget the times t. Okay. So, and then what is this? So we need to show that this is equal to tx. Or maybe we do backward. So what is tx plus t1? T, so we quickly do this. This one, t on this thing, and then t on the other thing. Let's try to do backward. Somewhere. So here, t on this, we got a1 plus 2a2 plus what? b1 plus, sorry, forgot the t, 2a, sorry, b2t. Are they equal? Yeah, they are equal. So they are equal by what? By associativity. So associativity is kind of important every time you see it. So this is true for associativity. Okay, so it is closed under scalar multiplication. Sorry, closed under vector addition. So next you can show that it is closed under vector addition. So let's say we want to find the matrix TB again. Okay, find matrix TB again. So let's see what we do, what we have. Okay. So the general rule is we have a map. Sorry, let me draw. So we have a map P2 to P2. Okay. Here transformation, right? Okay. Then we need to get the basis out first. So the question gives you a basis. Okay. You want to find TB, you need a basis. So we got a basis. Beta equals to 1t squared. Squared. Okay. So remember that we named the M, we named TB as the usual M. So M is what? M, you need to check on every basis what happened, and then you express in the basis in the codomain. Right, let me. We call this line here. Okay. So in this case, our V and W is the same. Two vector space the same, domain, codomain, and then two bases are also the same, right? Can see or not? Let me know if you can see. Okay. So so what we need to do is we need to check what happened to every basis. Right? Check what happened if you apply T to every basis here. Okay. So we write down what happened to every basis, 1, t, and t squared. So if you can't remember what's the linear transformation is, you need to write it down first. So let us write it down to remind us this. A1 plus A2 A2t. Okay. So in this case, if you evaluate T1, what do you get? A0 go away. A0 disappear. Okay, so T1 go to 0. TT, what's TT? T applies on T. You read the coefficient. Okay, so the coefficient is 1. How about T on T squared? So you read the coefficient and then multiply by T. Okay, so you get 2T. Okay, so far okay. Any question? No, so far okay. 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 Okay, some okay, some blur already. Okay, 0, 1, 2, T. Okay. So let's put it back here. So what's the coordinate vector for 0? Okay, so what's the coordinate vector for 0? Yep. What's the coordinate vector for 0? What's the coordinate vector for 0? Coordinate vector for 0. What do you get? 0. 0 vector, right? Hey, is everyone following? About TT? What's the coordinate vector for TT? Is it cannot see? Can you see or not? What's the coordinate vector? Okay, let's lay out step by step, okay? So what is 0? 0 is 0 times 1 plus 0 times t plus 0 times t squared. Okay, so the coefficient is 0. So what is 1? 1 is 1 times 1 plus 0 times t plus 0 times t squared. Okay, so you get 1, 0, 0. Make sense? Okay, how about 2t? 2t is what? 0 times 1 plus 2 times t plus. Okay, so what's the coefficient? Anyone tell? What's the coefficient? So 0, 2, 0. Okay, so you will get your basis as you will get your m as 0. Wait, 1, 0, 0, 0, 2, 0. Okay, so you express your linear transformation as this matrix here between this vector space. Does anyone recognize what this linear transformation is? Does anyone recognize what this is? You get this polynomial and then become this polynomial. What's this? Anyone can recognize? Anyone? Any idea? That side. Any idea? Derivative, yes. You take a derivative, right? So you differentiate with respect to t what do you get? Plus is equal to a1 plus 2a2t. Okay, so derivative you can write as a matrix. Okay, if you express in the right basis form. Okay, so you can use computer to calculate differentiation. Just use matrix if you have a right basis. Okay. Okay. So let me see. Okay. Okay. So if in the textbook, right, you can see that the geometry here is you go from R3 to R2. Okay. You Q one of the coordinate. Okay. So you go from R3 to R2. You kill one of the coordinate. Okay. So it becomes lower down the dimension when you do differentiation, which is correct, right? Because you lower down the degree. Just what you do. Okay. Okay. Next. So next. Similarly, we have a linear transformation again from R2 to R2. So we know that linear transformation we can write as matrix multiplication. Okay, this is what we have learned 2 weeks ago. Okay. Now it says that find a basis for R2 with the property that the TB or the M, okay, is a diagonal matrix. Okay. Can we do this? We do this. Can we do this? Have we diagonalized this guy before? I think we haven't, right? Okay. So maybe what time is it? 9:22. Okay, since this is a 2 by 2 matrix, right? So let's spend some time doing this, 5 minutes doing this. Try diagonalize this matrix. Okay, tell me what is P. Let's try diagonalize this matrix. This is just 2 by 2, so it's doable within the time. So let's try use the technique we have and see what's going on. Try diagonalize what is P. P such that A equals to PD. Okay, let's try 5 minutes, find out what is P. Yesterday, who is that? Zitang, huh? Is it Zitang? You, Zitang, huh? Zitang asked me, is there an easy way to compute this determinant here? A minus lambda I. I said don't have, because you must deal with the minus lambda part. So even if you do row reduction, right, you still need to divide by the long thing. So you can just do cofactor expansion. I think slowly, your skill of row reducing should be getting better. Because now we are learning new concept by using the OR method. So just keep brushing up the skill. New concept with OR method. Does everyone got the same as what I have? No. Everyone got the same? Yeah, got the same. Okay, cool. Okay, if you don't get the same, please voice out. So let's spend a while what we are doing here, right? So we got a T. Okay, let's write out the T from R2 to R2. So we got a T from R2 to R2, and then which is the matrix A. Okay, write down A. And then we somehow split A into P, D, P inverse. Okay. So what's this going on here actually? Okay. So really, this P here, right? Okay. You can understand it as a change of basis matrix. Okay. Change from where to where? So it's really changing from B to B standard. B to B standard. So should we recall what we do last time? So what is B to B standard? So B to B standard means if I apply the coordinate vector of B, coordinate vector with respect to B, I get coordinate vector with respect to B standard. Remember this or not? I hope this one is in your revision list. Use the change of basis matrix. When you apply to a coordinate vector with respect to B, you get coordinate vector with respect to B standard, right? Remember? Okay. So what is coordinate vector with respect to B standard? It's actually the vector itself. Okay. So what we can do here, this P is really changing from the B standard to B. Okay, so let me put here. So here we have a B standard. Let me put. I think you don't want to accept what I say, but this is true. So please go back and think of it. So we have a B standard here, and then we have a B here actually. So, all right. Yeah. Okay. Yeah. So what we are doing here is really, what we are doing on R2 is really between B standard. So we should move. We every time do between Rn is this part here, between B standard. Okay. If we manage to change our basis to B, okay, then we can replace the T as a D matrix. So this is a diagonal matrix. Okay. So what I'm trying to talk about is let's say you got, okay, maybe I write it down easier to think. So what I'm trying to say is if T, okay, if T is diagonalizable, then T is a diagonal matrix applying basis change, after applying a basis change on the vector space. And the basis change is given P, which consists of columns of eigenvector. So what I'm trying to do is let me put something. Okay. So what are we doing here? So what are we doing here is we got a linear transformation. Okay. Let's say this linear transformation is diagonalizable. Okay. Then after a change of basis on the vector space, we can make this linear transformation a diagonal. Maybe we call it a diagonal operators or just a diagonal matrix. Okay. Because after we make it into diagonal matrix is easier to study than arbitrary matrix. Okay, because the benefit I already told you yesterday, when you take power, when you take square, they are easier. Okay. Yeah. Okay. If you don't want to accept what I say just now, but accept this word here. Okay, accept this word. Accept after you accept this sentence here, go back and look, see what I'm talking about now. Okay. So if T is diagonalizable, then T is a diagonal matrix applying a basis change on the vector, and the basis change is given by P, okay, which is the column of the eigenvectors. So how you do the basis change to make it diagonal? It is the eigenvectors that give you the basis change. Change your basis into eigenvector. Okay. Yeah. Change your basis into eigenvector, then your linear transformation will act like a diagonal matrix. This is the story. Okay. Because original basis is not nice, not friendly to the linear transformation. The basis that's friendly to the linear transformation is the eigenvector basis. Okay. And accept. Okay. So this is another good thing of using eigenvector as a basis. If you change your vector space with eigenvector basis, then your linear transformation will become a diagonal. That is the matrix with diagonal entries on it. Okay. Yeah. Okay, maybe you don't see it immediately, but keep doing exercise, you'll see it. Yeah. Because this is your first time hearing, man. Right. Okay. Is it okay? Any question about this part here? So this is another thing you need to know today. So if you change your vector space into the eigenvector basis, then the linear transformation will act like a matrix. Okay. Yeah, this is just that's it what we want to do for this part. Okay. Okay. Next, we go to lecture 6. Not lecture 6, topics chapter 6. Let me find the 6. So we finished the eigenvector part already. Okay. So until the end, what we do is we found that if we use eigenvector as a basis, then linear transformation will become easy to express. That's all. Okay, chapter 6. Okay, chapter 6, we are going little bit back to like Euclid, how Euclid study geometry. So we need to draw some triangle and then look at the angle, look at the length. Okay. So for this chapter, this is this kind of example. So this chapter is about orthogonality. Okay. When you see the word orthogonality, what do you think? You know what the orthogonal means? Anyone know? Oh, don't know. Okay. So orthogonal means 90 degrees to each other, perpendicular. Okay, perpendicular to each other. So you might think, what does this to do with solving matrix equation, solving vector equation? Okay. So after we set out these tools, right, the orthogonality, later we will find solution to inconsistent system. Okay, maybe you think that doesn't make sense because inconsistent system has no solution because it's consistent. So what do you mean by finding solution to inconsistent system? Okay, this means we find the closest answer to that system. Okay, we cannot solve the system, but we find the closest one to the solution that we try to find. Although we cannot find, so we try to find the closest one. Okay, we cannot find, but we find the closest one. Okay, so this will use up the orthogonality. Okay, now it's 9:40. Okay, good. So what are we doing? So first we define is inner product. Okay, so I think first half of the in the class you asked me, can I multiply two vectors together or not? Okay, can I multiply two vectors together or not? Rn can and Rn can multiply together or not? Okay, today I tell you you can. Okay, to this inner product. Okay, so you see, I give you two vector in Rn, n times 1, m times 1. Okay. Okay, I think it's time to wake up because now it's a new one. So try. If you see your friend never wake up, please wake them up because this is a new part. So you can listen first. If you decide to sleep. But this is a new part. Okay. So 2 n times 1 vector, n times 1 vector. How you multiply? Okay. In the matrix, we always want this this part and this part the same n, right? Okay. But how you make it the same now? So you can transpose one of them. Okay. Transpose this one. So you get transpose the first one because we just want to get a number out. So transpose this one, we get 1 times n times n times 1. We get 1 times 1. Okay. This is what we're going to define today. It's an inner product of two. I think everyone should have seen this before, right? Dot product. Okay. When you first learn it, maybe is, at least for me, so when we do dot product, we just go this time this time this, and then add them together. Okay. So today, what I'm going to tell you is you can use matrix multiplication to define it. So u dot v is really, you turn the u around, u1 dot 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 up to un, then multiply v1 dot 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 up to v. So row and column. So okay. Okay, how about let's compute what is u dot v and v dot u. What is u dot v and v dot u? Yeah, let's try compute this. What is u dot v and v dot u? What is u dot v? UTV. Okay, try compute this. UTV and VTU. U dot v and v dot u. What's v dot u dot v? U dot v. A -1. Okay. V dot u. Also -1. Okay. So how do you compute? So you use the matrix multiplication. Okay. Row times column. 2 times 3 plus -5 times 2 plus -1, 3. Okay. So what happened to the bottom? 3 times 2 plus 2 times -5 plus -3 times -1. Okay. So from this calculation here, right, it's not surprising that why their solutions are the same, right? Because you see, when you multiply, you just swap the terms inside every summand. Right? 2 plus 3, 2 times 3 become 3 times 2. -5 times 2 become 2 times -1. -1 times -3 become -3 times -1. Okay, so they commute. Okay, so this inner product is commutative. Okay, we see it just now, and you can show that it also distribute. Okay, distribute, and also the scalars. The scalars. How shall I put the scalars? There's associative. Associative, and then you can multiply the scalar in. Okay, no matter where you put the scalar. Okay, and then the last thing is very important, quite interesting. So if you take dot product of two vectors together, it's always greater or equal to 0. Okay, we are interested in this kind of number, greater or equal to 0. Okay, because like length is always greater or equal to 0. You cannot have negative length one. If negative length, you cannot see. Okay, so we're interested in this kind of values here. U dot u is greater or equal to 0, and u dot u is equal to 0 if and only if u is 0. Okay, this one is also important here. Okay, you might think very trivial, but u dot u equals 0 if and only if u equals 0, meaning only 0 dot with 0 can have 0. Because sometimes you can have non-zero things put together and it becomes 0. Okay, but this is not true in this case, right? For vector addition, you can have, okay, just for number you can have what? Okay, cannot. Let's say if only in different world we can have, but in this case we don't have. So u dot u is 0 if and only if u is 0. Okay. Yeah. Yeah, this point, you're gonna study more maths or not, but this part here is very important for mathematics. U dot u is 0 if and only if u equals 0. Because in Einstein relativity, right, there's something when they're dot together, they are not the same, they are not equal to 0, but when they dot together, they get equal to 0. That's all. Okay. Okay, next. So actually, what is u dot u here? Okay, when you dot yourself, what do you get? Okay, let's take for example, let's take u equals to u1, u2. Okay, let's say we take u dot u. What is u dot u? As u dot u. You take u transpose times u, okay, as a matrix, you get u1, u2 times you dot these two together, what do you get? u1 times u1 plus u2 times, which is u1 squared plus u2 squared. Okay. So does this looks a bit like the Pythagoras theorem? Yeah. So we define a length of a vector to be the norm of v. Okay, we call this a norm. Norm of v is equal to square root v1 squared plus v2 squared plus up to vn squared. Okay. So if we define the u dot u to be the norm of u squared equals to u1 squared plus u2 squared. So we define this thing, okay, as u dot u. As u dot u. Okay. And then if we square root both sides, we will get the length. Okay. So remember that when we dot together two things, right? Okay. So this is the function from where to where? So this is a function from Rn to R. Okay. Rn to R. So I give you, okay, let me back out a bit. So we got this function here. Just now we got an inner product. Okay, put a dot. So a dot from Rn times Rn go to R and 2. So this is the first one, this is the second one. First we got a multiplication. So I give you 2 Rn, you give me 1 R. Okay, you split out one real number. Then now I give you one vector, you give me 1 R. Okay, so what's the meaning of this R? The meaning of this R is actually the length of the vector. Okay. We define it as the length of the vector. Okay. Yeah, so if you want to relate back to the Pythagoras theorem, let me draw it. So Pythagoras theorem, if you have a 0 here, then if you have a u1 here, you have a u2 here, and then this is the length. The vector of u is actually u equals to u1. So yeah. Any question on this len here? Maybe you don't have example, is it? Let me give you an example. Example. So for examples, is okay. What's the length of 2 minus 1 here? So compute the length of these two. So what's the vector 2 minus 1 here? Okay. 2 minus 1 here should looks like something like this. So here is 2. Yeah. So you need to go downward. Minus 1. So I have to go downward. So how you compute the length of this guy here? So if you just have elementary maths, maybe you can form this triangle here, right? And then you know that the length of the horizontal line is horizontal part is 2, and then vertical part is 1. Okay, so you will take 2 squared plus 1. If you want to find C equals to this. Does this make sense? Make sense? Okay, good. Okay. So this is square root 5. Okay. But just now we learned that how to compute this norm here. Okay. So this norm here is the square root of the inner product of the vector with itself. Right? Remember this. So let me write down the formula first. So just now we have that u norm of u is equal to u dot u. Okay, remember this. So I just put this square to the other side. So when you dot these two together, what do you get? You get invert the first one and then multiply with the second one. Okay, and then you get square root 2 times 2 plus minus, which is equal to 4 plus 1, which is square root. Okay, you can see that. What can you see here? You see, we make this minus 1 into 1 because we just care about how far. So we modulus it. But you can see how this inner product get rid of this troublesome here. Because every number square, you become positive. Yeah, this is how this inner product get rid of negative number. Okay, then it really compute the length. Okay, 55 minutes, right? Can we go a little bit more, and then the last 3 minutes we will have quiz. Okay, we go a bit longer, and then we take a break, and then we have quiz. Is it okay? Okay. 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 So let's go a bit longer. So for example, maybe this one I don't want to go into first. This one you can try as a homework. If important, I will bring it out again. This is just using linearity, using property of the norm. Because I think you guys get enough with this abstracting. So let's do something concrete here. Okay. So let's have this vector here. Okay. And then we want to find a unique vector. So what's a unique vector? Use what's a unique vector yet? Okay. So I should define what's a unique vector first. So let's define what's a unique vector. Definition. A unique vector is a vector with length 1. Okay, so that is, if we call it V, that is the norm of V is 1. Okay, unique mean 1. So where's the 1? The length is 1. Okay, unique vector. So it says that find a unique vector in the direction of V. Okay, so what does this mean? So let's draw some picture here. Maybe this doesn't represent R4, but just have a schematic description. So let's say this is V. Okay. So how do you find a vector in the direction of V with length 1? Any idea? Huh? Any idea? Yes, first of all, let us see what if this is already unique vector, a unique length, right? So let's see what's the length of V. Okay, what's the length of V? What's the length of V? You take square root V dot V, right? Okay, so what's the square root V dot V here? So you take V transpose times Vt, right? So what's V transpose times Vt here? Okay, so the main thing you want to remember, at least for this section, right, is this part here, okay? Length of V is equal to square root V dot V, okay? This part is the one you need to memorize for now. Later you can make sense of it. So what is Vt dot V? And then take square root. This number here. 1 plus 4 plus 4. So it's square root 9 equals to 3. Okay. So the length of this is 3. So it's not 1. So how to find a vector with length 1 in that direction? Any idea? Any idea? So this vector have length 3. So how to make it length 1? The direction is correct, but the length is wrong. How? How? Huh? Divide each entry with 3. Okay, let's try. Divide each entry with 3. So let's divide it by the length of the vector. Okay, see what we have. Okay, so if we divide all the entry with 3, so we get 1 over 3 on 1 minus 2. Okay, so maybe let's just check the length again. So let us check. Let's check. No space. Let's check. So let's check here. So let's check. So what's the length of V divided by the... So what do? We do the square root V over the norm of V dot with V norm of V, okay? Which is what? Which is we take 1 over 3 times 3 times the inverted one, and then multiply the vertical one. Right? Okay. So what do we get? We get square root 1/9 times, which is 1. Okay. Yeah. So to find unit vector, you just take your vector divided by the length of the v. I think this one also should have done it before. Okay. Okay. So how about we stop here first, and then we will continue tomorrow with this inner product business. So let's take a break until 10:13, and then we'll come back for quiz.
你是怎么找来的？
那个
Table 5。对，它的零可能有个 t 等于那个，我没听到
t 等于那个零。OK 这样，你说这个
这个怎么的这个？
对，因为你这个一嘛，1等于1加0乘这个加0乘这个嘛，对不对？
所以它设的是a 等于0
，a 0等于0，a 0就把它去掉。
为什么它等于？
你看，a 0这里有东西，没有东西，所以它把所有的 a 0送去，没有东西，所以就变成0了。你看 t 是什么 ？t 是0，a 0是0，a 1是1，a 2是0。OK， 你看它送过去有谁 ？a 1，对，有1，a 2是0嘛，所以这边是0哦。
a t。这道题的下面。
Yeah，
对，所以现在是 D， 它是怎么走？
这个 D 怎么得出来？这是昨天学的，就是说 D 的 diagonal entry 是它的 eigenvalue。
对，这个什么是50不是0，不是5003，有可能是3。
啥呢
30。
你说为什么不是5030？因为它这个 D 是昨天我们学了，就是它一定要是 diagonal 的。
对。
对 diagonal 的话就。diagonal 嘛，它就要diagonal 就 diagonal。你要想它打 triangle 也可以，它反正就是这一个 diagonal 线，就是第一个要在第一个 diagonal， 第二个的话就要在22，然后第三个就要在33、44、5。
这 standard 的东西，
这个 standard 有什么关系哈？有什么关系是不是？我这个是想说，你可以把这个 P 想成一个 change of basis。change of basis matrix， 然后怎么想呢？你应该要把它想成是从 B 去到 B 线的 ，OK？ 然后这个 B 对应的是我们还不知道什么 B，但是 B standard 我们知道，就是那个1001啊 ，OK？ 如果我们这样子想的话，是不是？
对。
这样的话你看这两边有 B 我不知道什么 B 啦，暂时 B， 然后 B 去 B standard，
对
，OK， 然后这一个是我们的 A，这个复杂的 A，然后我们就可以，其实我们可以用这个 A 来用 D 来表示，是一个 diagonal 的 matrix， 比较简化。 OK，然后这样子的意思是说什么呢？这个 P 是用什么做的 ？P 是用 Eigenvector 做的，所以意思说啊，这个 B 啊 ，OK， 如果你忘记的话，你应该要记这个东西。所以这个 PB 的是什么东西？PB 是说 B1 express 在 B standard， 然后还有 B2 express 在 B standard。你如果忘记这个 formula 的话，要去看一下。所以它这里的 column 是什么？它是 B 这里面的 basis express 成 B standard 的样子。
对。
所以其实说了什么意思？其实是什么意思？其实就是说你从 B standard 转换成这个 matrix 啊，这个 vector， 从这个 basis 转换成这个 basis， 这个 B 就是 B standard。其实这个就是 B， 其实这个就是 B。OK， 可能我太快了，因为为什么？你看这个 express in 这个是什么？其实就是 B1 本身跟 B2 本身。像我刚才讲的，所有东西 express 在 B standard 就是它本身，还记得吗？还记得吗？你看这个等于这个，所以你取啊，所以你看它口诀又是它，所以它就是 B1 跟 B2 本人。所以说什么？所以如果你把 B standard 换成你的那个 Eigenvector 的 basis， 你的 transformation 就会变成一个 diagonal。这么复杂哦，那你只用这个表示就好。
所以这里 P 是
这个 P 怎么得出来哈？这个 P 你就要去找那个什么 null space 啊。
这里是
你要去找它的 eigenvector，找5的 eigenvector 是什么？找3的 eigenvector 是什么？这要去 solve 那个 null space 哦。a 减 5i a 减 3i，
所以它得出来不是对吧？得出来是这。
对，这个的 parametric vector form， 这个的答案是什么？这个的 free variable 在哪里？在 x2 嘛，对不对？
x2 对。
所以 x2， 然后你怎样读它的那个 solution 出来？怎么读它 solution 出来？这个是 s1 加 x2 等于0。说 s1 等于重复那个步骤。
A，先问的这个，
好，这个
它是什么含义？
定义也分 sin， 呀，
P 0等于0是什么？
就是在0点的时候还是0。
那这个 P 是一个向量，然后它同时看成一个函数，还是？
哎，对，
它是一个向量，然后同时看成一个。
对。
那这里说这个法则它为什么会有？为什么一定能够拆开？
这是我们定义啊，
我没有定义。
我们上课定义过 Pn 里面的加法。
但是对，而且上课的时候讲的跟这个也不一定是一个，题目里只说 P 是，这题目只给这2个条件，没说 P 是什么东西。
你说 P 是什么？37啊，不是，我是说我们应该定义过它们怎么加。
就是我的意思，这里能够确定它能够拆开，是不是要先说一步，说它是 linear transformation， 说它是 one to one one to 的？
没有，这个就是 matrix 相加吧，polynomial 相加吧。polynomial 怎么相加？它只是跟 polynomial 怎么相加有关系吗？
是，但是那就是这样怎么理解这个 f_p 的？
P 就是比如说，
如果它是
P 如果长成是1加 t square 的话，P0就是1加0 square。
那这个 P 是可以理解成多项式，还是理解成函数？理解成多项式我觉得可以，但是理解成函数的话，
函数也可以，
不一定可以这样。
函数也可以，函数也可以，
所有都可以这样。
可以。比如说，你看所有的，
就像比如那个函数，
这是我们定义的。我们定义函数相加就是函数本身在那个点的相加。 这是我们定义的。
就在那个
你记得我们有定义那个 vector space 的时候呀
那这个就先这样。还有那个，
呀
这个东西它是一样是
呀
这个是 subspace，vector
呀
space。
呀呀，
空集算是一个
谁的 vector space？
不知道。
不能你要活
Vector
在
space
你 subspace 一定要活在一个 vector space 啊？
它是 vector space，
哦，我没有写出来是吗？还是这样 ？OK，别紧哈。
它是 vector space。
你要哦，你说它是不是 vector space？
空集算不算一个零 vector？
你要定义我
定义
呀，要定义。
定义了就行。
对你 vector space 你要有一个 set，然后你要怎么相加，然后你要怎么所以你要告诉我 empty set 跟 empty set 要怎么相加咯，然后可以，然后你要怎么乘那个 scalar 进来，所以什么是2乘 empty set，你要告诉我什么是2乘 empty set，什么是3乘 empty set，什么是各种各样的乘 empty set，然后这些东西都要活在这个 set 里面，所以你这个 set 只有0就 empty set 了。那2乘 empty set 是什么？还是 empty set 的话，这样你就要这样 define 咯。这样你这样子 define 起来，这个就是一个 zero space 嘛，就是跟 zero space 一样。
zero space 也是这样。
zero vector space，yeah。
然后只有一个空集，它是不是 vector space？
一个空集它就不是一个 vector space。
要是它这个
是啊，是 vector space。赶紧去，赶紧去。好，开始了，赶紧去。
Okay, can I get the first person to volunteer and count how many person in your group, then come and collect from 4 groups. Okay, a lot of people ask me can use a calculator or not. You can use calculator, but you cannot use the calculator that can like the computer matrix, do matrix calculation. You just can use scientific one. Okay. 你算张总，张总算啊，张总算，赶紧来，他去厕所啊。If you need a draft paper, I can give you. Fourteen. Oh, one more absent again. Every time we must have one absent one. Don't start yet. You can read yet. Read first. Write down your student ID. We will start together. Read. You can write your name, student ID. Don't start yet. Let's start together. Who is absent today? Hey, Joey haven't signed. Sign. Who is absent? Anyone absent today? Why? Or not enough? Maybe someone come wrong. Huh? Extra. Hey. Did everyone got Not enough? Not enough? Okay, I think everyone come today. Okay, good. So we don't need to make the online one. Okay, so what time is it? 10:17. Okay, let's stop at 10:47. Okay, you can start now. Make sure you get quiz 3. I'm not sure why I left 2 here. Make sure you get quiz 3. 10 more minutes. 10 more minutes. Never. I know they are your friend. Please don't cheat. Okay, please don't. Just use the time to think. Everyone was tested in the same condition. I don't want to have people cheating. I can catch you if I want. Please behave yourself. Please use the time to think. You guys need more time, so okay, done. Need more time, so done. Huh? Okay, 5 more minutes. Because people need to come in. 5 more minutes. For those who are done, please check your answer, check your solution, check your ID, check your name. Guys, think. Okay, think. The definition should be natural. Okay, while waiting, check your answer, clean up, check your name, solution. Okay, please pass to the front, and then the first person, please help me to count